Hello, everyone. I just wanted to spend a little bit of time and go through some of the mesh settings in a recording so that you have the ability to review them later, as well as hopefully you'll have better ability to read all of the text at least once the video resolution, is processed at the higher level or whatever YouTube does. So, we have the same thing we've looked at in a previous video, same thing we looked at in class. We have three parts. We have a downstream cylinder, we have a conical nozzle, we have an upstream cylinder, and these three are united into one piece. And then half of it is cut away with a block, so we wind up with a two-dimensional domain on the half plane, which looks as you can see here. Right, effectively a rectangle on the left, a converging section, and then a rectangle on the right, and an outlet. So this is our domain. That can all be seen under parts, and this unite and subtract are the operations that physically construct this. We united the downstream, the nozzle, and the upstream section, and then we cut away half of it with this block to form this subtract. So actually, I'm going to rename this really quickly here, 2D domain. So when we're setting up for 2D meshing, there's a couple of important things. With 3D meshing, this step isn't needed, but for 2D meshing, it is absolutely required. You must have the plane, the two-dimensional plane that you wish to simulate, parallel to the XY plane and located at z equals 0. So if I go up here to this measure tool and I measure any 2 points on here, you'll see that it spits out exactly 0 for z. That is, this plane that we're looking at here exists at z equals 0 and is parallel to the xy plane. The xy plane is what it is simulating. So to tell it that this is what we're simulating and that we're only doing 2 dimensions, you must create an operation, new mesh badge for 2D meshing. When you do that, you select the part that you're trying to create the 2D mesh on, in this case, this 2D domain part. If you called it something else, you would select the other name, right? But you select the part that has the plane that you want to simulate. So let me just change this really quickly here so it thinks it needs updating so we can take a look at this. So if I execute that, so if I execute the badge for 2D meshing, you'll see that it does a really quick operation. It says badge for 2D meshing complete. If it doesn't say anything about an error about it not being able to find a plane at z equals 0, you should be okay. If, for example, let me do something like 0, 2, 0, 1. So if I attempt to execute this now, it should give me an error. So you see it says the following parts do not have any surfaces that are coincident with the 2D z equals 0 plane. Because I moved over the edge of the block that we were cutting this with, it doesn't actually have an edge at z equals 0 anymore. So it says the operation is still completed, but it really didn't. There is no two-dimensional domain. If I put this block back to exactly 0 and run this again, you'll see it will complete without the error. And notice, if you're looking really closely, the 2D domain has this little red dot that shows up next to it, showing that it's actually two-dimensional. When this operation failed, that dot was not there because it was not actually a two-dimensional domain. Most things, although maybe not quite everything we do, will be confined to 2 dimensions for this class to keep things computationally simple. However, the same principles apply to 3 dimensions. It is just harder to verify because it's a lot harder to check things in 3 dimensions than 2. Now, once the badge for 2D meshing operation is complete, again, you'll see this little red dot show up showing you that it's successfully completed on whichever part you pointed it at. We need to actually create the mesh. You can see one up on the screen currently. Blow this up a little bit so it's more visible. However, if we didn't have one of these, you would need to go to Operations, New, Mesh, Automated Mesh, 2D. For a 2D mesh, you select Automated Mesh, 2D. Fairly straightforward. This is kind of the general purpose mesher inside of STAR-CCM+. There are, let me actually go back to operations real fast. There are a couple of special case meshers, directed mesh, turbo machinery meshing, volume extruder, I believe, kind of does that. Patterning volume meshes, various more advanced things you can do, but automated mesh 2D and automated mesh 3 dimensions are kind of the general purpose ones. So, what do we have here? Well, actually, you know what? Let me just go ahead and delete this and we'll start from scratch. So, new mesh, automated mesh 2D. The first thing is you need to tell it which part do you want to mesh. We've only badged one part for 2D meshing, so we only have one part to select. So we should select that part and go through and select some meshers here. So I'm going to, for the moment, select polygonal mesher. What I will do later is after we've talked about some of the controls, which principally apply to pretty much all of them, we'll take a look at what does the quadrilateral and what does the triangular mesher look like. But we're going to start with polygonal and move from there. So polygonal mesher forms a mesh that, you guessed it, is polygons. We've seen this, we've talked about this. And we also can optionally turn on the prism layer mesher. In most cases, it's really not all that optional. Prism layers are used to model boundary layers. Boundary layers occur pretty much everywhere to a significant enough degree where they're going to matter. So we're going to want to turn on that. And we see this automated mesh node show up on the left-hand side here. You'll see that it under this meshers folder, so under our automated mesh 2D, it has 3 folders: meshers, default controls, and custom controls. Meshers, it tells you what meshers you've turned on along with a couple of properties for them. So we can see it has some properties for the polygonal mesher. It has some properties for the prism layer mesher. These are typically more advanced properties that you don't need to mess with all that much. But if you get to the more advanced level where they start mattering, then you can adjust some advanced settings for the entire prism layer right here. So, default controls is, you guessed it, the default that it will attempt to use everywhere in this mesh unless you tell it otherwise. These apply, again, everywhere unless you've used this third folder, which is custom controls. Custom controls will let you specify different settings to use in different parts of the mesh. Because very rarely will one type of mesh work perfectly everywhere. There's usually corner cases, literally and metaphorically, that involve some amount of customization needed in order to get them to work properly. So let's talk about these default controls. Base size. This one is very, very important. This is the size that everything else is relative to. I recommend making this on the same order of the maximum cell size that you want for most of the mesh. So for something that has a 10 centimeter radius on the left here and a 5 centimeter radius on the right, we probably want this to be somewhere on the order of 1 centimeter, maybe even smaller, but we're going to start with 1 centimeter base size. If you see a percentage in meshing controls, it is relative to base size. 100% of 1 centimeter is 1 centimeter. 200% of 1 centimeter is 2 centimeters. 50% of 1 centimeter is, you guessed it, half a centimeter, etc. CAD projection. This just says that if you have a CAD definition of what this looks like, it will try and make sure the edges of the mesh actually fall on the surface defined by CAD. It tells you that right here. Project vertices to CAD geometry where available. That it's just saying if there's a little corner of the mesh somewhere that's close to but not directly on where the CAD is, it will move it so that it is on the CAD geometry to try and make sure you're actually meshing what you modeled as precisely as possible. It's on by default. You should probably leave it on by default. It's only in very weird circumstances where it might hurt anything. And it's a marginal slowdown at best. It really doesn't slow things down very much. Target surface size. This is a little bit of a misnomer. It's really more of a maximum surface size. This is the largest it will make a cell on the surfaces by default. Again, target surface size, to reiterate, is effectively the maximum size on the surface. Well, what do I mean by on the surface in this case? This applies to both 2 dimensions and 3 dimensions, is that the way the meshers work is they start with a mesh on the surfaces. On the boundaries of your model. And then it will let these meshes either grow or shrink depending on properties as you move away from the surface. So it's saying at this surface, it's going to make sure that these cells have a maximum edge length of 1 centimeter. So these are probably, well, actually, I don't know what these are at the moment. These are actually half centimeter because I think I used a smaller mesh before. Yeah, these are pretty much half centimeter exactly. Minimum surface size is same thing as maximum, except it's a minimum. Or it's the same thing as target, except it's a minimum surface size. This is the smallest it will make any cell. Regardless of any other refinements you tell it, that is the smallest it will ever let a cell be. In this case, 1 millimeter in size. Oh, no, that still applies. So again, on the surface, the smallest it will ever let a cell be, left to right, in this case, along the surface, will be 1 millimeter. Surface curvature, well, this one's a little bit hard to show in this case. Actually, here, tell you what, let me add something to this so maybe I can demonstrate this. Also, let me save this as a new version. Okay, let's go ahead and add a new sphere we're going to add this as a 5 centimeter radius. We're going to add it at X location 30 centimeter. Excuse me. This needs to be at 60 centimeters. There we go. I'm going to create that over there. And we're going to add it to our Unite. And actually, tell you what, I'm just going to delete this really quickly here. Take this 2D domain and make a new region for it. Wait a second, where? There we go. I don't know why, but this window keeps on popping up outside of the monitor that STAR-CCM is on. So one region for each part, one boundary for each part surface. And click apply, and we wind up with a region. So this is our new outlet. I'm also going to create a new mesh scene. So our outlet, this sphere surface are both pressure outlets. And then our inlet is a velocity inlet. So what was I saying? We have the target size, and actually I'm going to turn down this base size. We're going to make this 0.5 centimeter and run it again. Execute. So what does this, let's see here, align view on the surface. What does this surface curvature do? Well, to demonstrate visually and to explain it a little bit, computers don't do circles. They do straight lines. They approximate circles with a whole bunch of straight lines. This is saying how many straight lines are allowed to make up a full, or the minimum number of straight lines that you're telling it to use to make up a 360-degree circle. So right now, it is going to make sure there are at least 36 straight lines per 360-degree circle. That is, one line can span no more than 10 degrees of angular displacement. It can have more, and if you run into the minimum size requirement, it can also have less. But it will try and make sure there are at least 36 lines available. So let's go ahead and make this 72 and see if this circle changes any. It might not. Ah, yeah, you can see those got a little bit smaller. Here, let's make this something a little bit more ridiculous. 144. Execute. Ah, they got a lot smaller. You can see it's putting more lines in here to more accurately approximate this circular arc. So realistically, 36 is usually okay for most applications. I'm going to go ahead and just leave this at 36, but you can tune that up or down depending on how accurate this circular arc needs to be. I mean, to me, this looks pretty darn circular to me as it is. You really don't need to refine that any. But if you wanted to, you could refine that. And there's even a little checkbox here to say, hey, the maximum distance you can move off of this circle is some amount. So if you activate that, you get a couple more options. Usually you don't need to mess with these. Usually just having the default 36 points per circle is enough. If you want it to be more accurate, you could turn that number up. It's usually not necessary. Surface proximity is making sure there is some number of points, or making sure the maximum cell size on any surface is enough that you could fit so many cells between those two surfaces. So right now, by default, this is going to just be 2. It says, hey, I want to make sure you can get 2 cells in between any 2 adjacent surfaces. Which is great. You probably want more than that in most cases, but the default is 2. Right now, we have so many more than 2 that this is not coming into effect. So let's go ahead and crank this up to something fairly ridiculous like 50, just to demonstrate. Yep, you can see all the walls got a lot finer, and the cells back here on the left are actually coarser than the cells on the right. That's because there's more distance here, so the cells can be bigger and still fit, what did I say, 50 cells in between this distance. We could also keep on cranking this up, and it'll make them smaller still to a point until we bump into the minimum cell size. So at this point, they're probably not going to get any smaller because we're probably pretty darn. Oh, actually, they got smaller still. Okay, let me keep on cranking this up until we run into the minimum cell size. So theoretically, at some point, these will stop getting any smaller. Oh, yep, there we go. You see, these didn't change. These changed a little bit because we're at this point where these cells are already 0.5 millimeter in size. So let's check that. Oh, yep, look at that. That is 1/2 millimeter in size. So these cells are already as small as they can get, and they won't get any smaller because of our minimum cell size. Sorry about that. There we go. The cells over here could still get probably a little bit smaller. They might have just gotten as small as they can be. No, not quite. They can still get a little bit smaller over here. Not by much, but a little bit. So in practice, like 5 or 6 is probably a good number for that, assuming you know that you don't have too many surfaces, or you can go up to like maybe 8 if you have something where you know you have a whole bunch of closely packed surfaces that matter. But in theory, this shouldn't matter a whole lot because you're not putting surfaces very close to each other, right? Unless you need to, in which case you have to. Surface growth rate. This one is especially important for 2 dimensions. So I was mentioning that minimum and target size are only on the edges. We can see that because very clearly these cells get quite large in the middle. As a matter of fact, they get far larger than 0.5 centimeter. This cell in the middle here is like 1 inch across, give or take. A little bit more than 1 inch across, actually. So what surface growth rate does is it says, hey, these cells out at the edge here, those are restricted to a specific size based on the target size, the minimum size, and all these other parameters. But they're allowed to get larger as they move away from the surface, or smaller as needed. So that is what the surface growth rate controls. By default, they can change size at, I believe, 30%. That is, each cell can be 30% larger or smaller than the adjacent cell. That's pretty fast. We can tell it to grow more slowly. And we should see these in the middle get much smaller. Oh, yep, much smaller. We could also say surface growth rate could be really fast. Let's see what this does. Oh, now they're really large. We could also customize this and say, no, I want to define how fast these are growing. So I want to say, let's go with, 5% growth rate. Should be relatively slow. These should remain mostly the same size at the edges here. They'll be larger, but not by nearly as much. Yeah. So each cell is growing by 5% as it moves out towards the middle here. Then we have number of prism layers. Well, let's zoom in, and we can see a prism layer. These two layers of cells right here. Actually, let me look at the bottom, just so my nomenclature is going to match a little bit more closely with what we're looking at here. So this is a prism layer. Right now, we have we have three specifications. We tell it how many layers of cells there are. Right now, there are two. We tell it how big each layer is relative to the last. So 50% means this second cell should, in theory, be 50% as thick as the first cell. So this looks like it's about a millimeter, which means that first cell is probably pretty much exactly 2/3 of a millimeter thick. Makes sense. Checks out. The second cell is 50% thicker than the first cell. And lastly, we get to customize how thick is this prism layer total, top to bottom. By default, it's 33% thick. That's usually okay for most circumstances. Somewhere between like 30 to 75%, or maybe a little bit more broadly of like 25 to 75%, somewhere in there will be about right depending on your mesh settings. The way you can look at this and basically say, okay, is this about right? Is a couple of things. The prism layer stretching of 1.5 is generally okay to leave alone, but you will need to mess with the number of prism layers and the total thickness. So usually the first thing is the number of prism layers. And this is determined by how much do you care about what's going on in the boundary layer. If you don't care all that much, I would recommend, maybe probably about 4 minimum prism layers. Now there are 4 prism layers. However, that's not the end-all be-all of this. So how precisely do you need to model the boundary layer? If you really care, you might need something more like 16 to 24. If you really care a lot, you might need something like 16 to 24 prism layers. Based on how much you care, you're going to wind up with some number of prism layers. I'm going to leave this at 4 for the moment. And I'm going to turn down surface proximity to something slightly more benign of 100. So this runs a little bit faster. There we go. And the next thing to look at or to modify is the total thickness. And the way you'd look at this is you would pretty much look at this boundary layer and say, great, how big is this cell relative to the cell next to it? And the answer in this case is actually very close to the right size. If we look at the characteristic cell size of these cells immediately out here, they're about a millimeter to a side. If we look at this of this last prism layer, it's about 0.7 millimeters. That's pretty close. That's a pretty smooth transition from the prism layer to what we call the core mesh, anything outside the prism layer. This is the sort of transition you generally want to see. You want to see that this last cell has an aspect ratio of close to 1. And it's not going to be exactly 1. In some cases, it's going to be, 2 or 3. But you don't want to see an aspect ratio of like 10. By that, I mean, let's turn this down. Turn down the prism layer thickness just to see what you very don't want. This is what you don't want. You can see this size adjustment is enormous, and these cells are really long and skinny. This is bad. This is not what you want. You want something a lot closer to what we had before. So the aspect ratio of this cell, if I had to guess, is probably somewhere in the neighborhood of like 7 or 8. Let's see here. It is about a millimeter left to right, and it's actually closer to like 12 or 13. Interesting. Yeah, it's a lot closer to like 12 or 13. It's about 1 millimeter left to right, and it's about 0.07 millimeters tall, which means this thing has an aspect ratio of, like 12 or 13. Maybe even more like 15. That's a pretty bad aspect ratio. Whereas if we turn up the prism layer thickness, we can kind of control what that aspect ratio is based on the number of prism layers we have. And now this is pretty close to an aspect ratio of 1. Not exactly, but close. We have, it's 0.8 millimeter, 0.83 millimeters tall and 1 millimeter wide. That's pretty good. And also, this size transition to the outside is relatively smooth. If you have an aspect ratio of about 1, this size transition from the last of the prism layers to the core mesh should be pretty smooth. This will, however, change if we change up how many prism layers we have. If we have 12 prism layers, suddenly this isn't going to look quite as reasonable. Still looks reasonable-ish, but less so, right? Instead of an aspect ratio of close to 1, this is probably an aspect ratio of like 2 to 1 almost. It's like an aspect ratio of 3 to 2. Not as great. Still manageable, but not as great. If we had to have like 24 prism layers, because we really, really cared about the boundary layer. And this actually still looks pretty reasonable. It's pretty insensitive because this last cell thickness is based exponentially on all the previous ones. You can see that there's very thin ones. And you will get very thin ones at the bottom here. But this last cell and this transition is kind of the important part. So I'm going to turn this down to a more benign 8 prism layers. I'm going to return surface proximity to something reasonable like 20. And honestly, this looks like a pretty reasonable mesh. However, this is a fairly simple configuration. Let's talk about what we do if we don't have something so simple. If we need to make specific adjustments to specific areas. This gets into custom controls. We have a couple different options. We can control things on a curve. Let's see here, do we have any curves to select? Let's see here. So in 2 dimensions, you can effectively think of everything as a unit depth. So in our particular case, this curve is actually 2 points at the top and bottom here. If we select a surface, this is actually going to be a straight line. So if we select, let's say, our inlet, this is a straight line. This is our inlet. We could also select an entire volume. We can say, do something to every cell inside an entire volume. So everything inside of this area would have something done to it. Curve controls, I basically have never found myself using, so I'm a little bit fuzzy on exactly what they do here. But let's go ahead and try and see if we can modify anything in this area here. So let's first realize that for any custom control, you have to tell it a couple things. You have to tell it what you are modifying, or sorry, you have to tell it what type of control it is. So you create a new control. Are you controlling a curve, a surface, or a volume? In 2 dimensions, you can effectively think of this as losing 1 dimension from each of these. A curve becomes points, a point or multiple points. A surface becomes a line in 2 dimensions, so it can be curved, or multiple lines. And a volume becomes an area. So you tell it which type of control you want. Once you've made that type of control, you tell it where you want to control this thing. What curve or what surface or what volume do you want to control it? In this case, I've selected a line that technically exists in 3 dimensions because it's this half circular arc, but in practice, because this is a 2-dimensional line, it only exists at 2 points. Right at that corner and right at that corner. So you tell it what type of control, where/what location you are controlling. What about the mesh do you want to change at that location? Okay, this is under these controls. This doesn't actually modify the value, but this says, hey, I want to change these things. Or more importantly, by default, it says, I don't want to change these things. Target surface size, it's just going to use the default values if it says parent. Minimum surface size, same thing. If you want to specify an anisotropic surface size, that is a uniform surface size, you can check this box and you'll get some values to mess around with. You can change any of these to custom and you'll get some values to mess around with. So let's change both the target and the minimum. So I've changed target to custom. I've changed minimum to custom. This says, hey, we are changing something about the target surface size and the minimum surface size. So you, again, start at the top level for any custom controls. What type of control is it? What location are you controlling? Oh, interesting. What location are you controlling? What about the mesh are you changing at that location? In this case, the target surface size and the minimum surface size. And then how are you changing that value? So let's go ahead and set this target to, let's say, 20% of the base size and the minimum to 5%. And let's see if this does anything. Execute. Ah, you see, in this corner, it made the cells really small. Let's make this something ridiculous like 1% and 5%. execute. Really small. So you can see it's making the cells, excuse me, very small in this corner. And they are growing as it moves away from the corner. It's growing by that surface growth rate. But in this corner, they're very small. We've controlled the cells in these corners to have a target size, aka maximum size, of 5% of the base size, or 1% of the base size for minimum. There's also another option. So we modify anisotropic surface size. We can modify a first layer thickness. So this is effectively a small layer, almost like a prism layer, but not quite, of cells adjacent to the surface that won't grow. This is saying nearby this surface, make some layer of cells that have some thickness. So let's say make, this may actually not do anything here because this is a point. Oh, it didn't like that. Okay, well, we'll not do this for the moment, and we'll come back to maybe that later. We'll see. But wake refinement is another major control that you can find great use for in a number of applications. Because you know that complex flow phenomena may not just occur on a surface. They might occur behind a surface. They might occur behind a body, behind a cylinder, behind an airfoil, behind a boat, plane, what have you. And that's what wake refinement's for. You tell it a couple of things. You tell it actually a whole bunch of things. So, first of all, is you tell it how far behind this point, in this case, we're talking about effectively 2 points here, this top and bottom corner. How far behind this point or surface do you want to make it this refinement? By default, it's 10 meters. 10 meters is pretty big. Let's make this like 15 centimeters. So we should see our wake refinement go about 15 centimeters downstream, so about halfway to this corner. Should go about halfway down this cylinder. You can tell it what coordinate system you want. Laboratory is fine by default. We're not going to mess around with too much with that for the moment. And you tell it what direction. So you can tell it, hey, positive X. Or we could tell this, no, sweep inwards along negative Y, positive X. You could do all kinds of things. You could also tell it how much you want it to spread out. So let's give it a 5-degree spread angle. And this will make more sense. 5 degrees. This will make more sense once we start to modify the values and mess around with it. So, how big do you want the cells to be? The isotropic size in this region, in this wake. By default, 25%. We'll leave that alone for the moment. Wake refinement, the growth rate, how rapidly will the cells change size in the wake, if needed? We'll set that to 10%. And let's mesh this and see if we can see what this wake looks like. Aha, you can kind of see what looks like a triangular region here, which is a 5-degree cone extending in the positive X direction from these 2 points. let's go ahead and just mess around with a couple of these things so we can see what's going on here. Let's go ahead and make this 25 centimeters. We expect this to move out right about here. Yep, pretty accurate. We went from 15 to 25 centimeters. We can also change, hey, we want this to spread out a lot more. Let's say 15 degrees. There is a maximum of 60 degrees, incidentally, but we're going to 15 up from 5. So we expect this to come out like all the way here or more. Yep, 15 degrees. So there's an inner triangle where the cells can't get any larger, and then the cells grow as they move away from that inner triangle. Let's see here. What else? We can specify the direction. Okay. Let's go ahead and say 1 positive x, but also negative 1 y. So this triangle should extend, well, for this lower corner, it's going to extend out of our domain. For this upper corner, it's going to extend kind of into the middle here. So let's go ahead and execute this. And you can see more clearly kind of that triangular region that we were talking about. So it extends from this corner out to, well, in a 15-degree cone, 15-degree half-angle cone, I should say, out to 25 centimeters downstream. We could change down the isotropic size, make those cells smaller. Oh dear, it's thinking about that one for a second. There we go. They got a lot smaller. Those are some pretty tiny cells in there. But you can still kind of see that core triangular region, and then it gets a little bit larger as it spreads out from there. You can also, if you decide you don't want to control, you can enable or disable them. Just temporarily to turn them off while leaving them there still. You don't have to delete them. So if you click on this curve control, under properties, you can see that it has a couple of things. In addition to selecting which curve are you controlling here, you can tell it, hey, let's enable this, which is enabled by default. Or you can tell it, now we're going to disable this control. I've just disabled that control. We're going to run this again, and we can see that that control has no effect. So if you want to turn a control on or off without getting rid of it entirely, you can absolutely do that. Now, let's look at what we have to mess around with for a surface control. We have a couple of the same things. We can change the target size. We can change the minimum size on a surface, which we're probably going to change. So I went ahead and turned those on. We can also mess around with surface curvature, which won't affect anything here because this is a straight line. We can also change surface proximity. We can disable it. We can make it a custom value. Edge proximity, we can disable it. We can make it a custom value. Surface growth rate, we can customize that. We can tell it whether to use polygons or quad dominant surface meshing. I'm going to leave that alone as parent. We can also, on the surface, we can either disable prism layers or we can customize them. If we want to customize them, we don't have to customize all the parts of it. We just kind of need to customize some parts of it. Or rather, we can customize some parts of it if we wanted to. You could customize the number of layers, the total thickness, the stretch factor. You can edit all of these things for a surface. So instead of selecting the inlet here, I'm actually going to select two things. I'm going to select the our sphere surface and our outlet wall here. And the reason for this is so we can see the effect of all of these on the surface. So let's go ahead and set our target to 50% here. And let's run this again. Uh, Wait a second. What did I change that it doesn't like? That's 50. Okay, let me see if I can figure out. This is a little bit curious. Let me see here. If I get rid of those, it works. Okay, so let's just try making a new surface control and see if this fixes it. Sometimes turning it off and back on again is really just the best way to fix a thing. So if we change our target surface size, let's say 50%, 50%, execute. Well, these got a lot smaller. Let's change that target size down to 25%. Also execute. Smaller still. Again, we're effectively changing the maximum cell size along these walls to now 25% of the base size. We could also adjust the minimum. So let's see if it throws an error for this. Yeah, I tried to make the minimum size greater than the target size. It didn't want to let me. We'll leave that at 10%. Surface curvature. We can customize the surface curvature and say, now I want a whole bunch of points on this circle. I want this to be a very, very accurate circle. Didn't seem to change very much. Why might that be? Did we run into our minimum cell size restraint? Well, this cells, let's see here, about 2 millimeters, so probably not. It might just be that we literally already have 200 points per arc. Let's keep on cranking this number up. Let's do 800. Okay, now I'm starting to question if this is doing what I expect or not. Let's try turning down the minimum surface size. Let's make this 2% and see what happens. I couldn't exactly tell you why, but this appears to not really want to modify our surface curvature control very much for some reason. Yeah, I couldn't tell you exactly why. I'd have to figure out it a little bit out later, but that surface curvature control doesn't seem to want to do anything really at the moment here. Let's see if surface proximity does. So let's make this 200. See what happens. That definitely made things a lot smaller. So the surface proximity did that, but it only did it here because excuse me, these are the only surfaces where we're controlling anything. We could also modify anything else that we wanted to. We could modify the prism layers. We could add wake refinement if we really wanted to. We could do all kinds of things. But the important thing is it only happens along these surfaces that we've controlled. And last but not least, I'm just going to turn off this surface control and rerun this here. I'm going to create a new volumetric control. Now these work a little bit different. Again, you have to select a volume. So in this case, I'm going to select the entire upstream cylindrical section. Everything inside of this cylinder will be controlled. We don't get as many controls when we talk about volumes. We can still control prism layers, but we get this 2D surface mesher node. So what we can say is, okay, we're going to customize this 2D surface mesher size. And we're going to say that, let's make it 25%. And let's run this and see what it does. So it made every surface, including our actual simulation plane, which is a surface, have cells with a target size, a two-dimensional surface target size of 25%. So inside of this region, everything is constrained to be no larger than 25%. You could say 50%, and these should get twice as large and stay there for the entire thing. We could also select multiple different regions. They don't have to be contiguous either. We can select upstream and downstream and mesh these both simultaneously. And we have small cells, and then large cells in the middle. Or we can select just the outlet section here. And we'll have everything be small at the outlet. We can turn this down again. Etc. So we probably really don't practically need any of these because this mesh already looked decent for a relatively simple configuration like this already. So let's see here. If I hit save for starters, will this run? It should theoretically run just fine. But that's kind of a crash course in meshing. Let's just see what this mesh gives us if we run this out. I'm not going through what this actually means just yet. I'm going to save that for a video a little bit later today, I think. But suffice it to say, this is kind of the gold standard for what you'd like to see for a simulation that is working. And let's see what this looks like. So total pressure is basically constant. Let's take a look at velocity magnitude. Pretty much just what we'd expect. We see constant velocity in, it accelerates. We get a little bit of a stagnation spike in these corners here. We get a little bit of a velocity spike as it rounds these corners here, but mostly it's uniform. So we've gone through this a lot, this particular example problem. This is a simple one, but it's a good one to start with because you can verify this with hand calculations. You can check a whole bunch of things very easily with this problem. So I'm going to wrap up this video here, and we're going to do 2 more videos, or I think we need 2 more things before we can actually start doing simulations. Taking a little bit, it's taken about a month of, 4 out of our 16 weeks. But we're very close to being able to hit the ground running here. Unfortunately, we kind of need all of the parts put together before we can really get started, but I'll save that for a future video.